talk about cabin atmosphere control systems, and let's start with pressurization. Now, the whole purpose, the whole idea of pressurizing an aircraft is to allow operation at high altitudes and create an environment to prevent hypoxia. Hypoxia, of course, is lack of sufficient oxygen reaching the brain, commonly caused by flying at too high an altitude without oxygen or without pressurization, because what pressurization does is allow you to fly at the high altitude without worrying about hypoxia. Now, when you pressurize an aircraft, you get a differential pressure, a cabin differential pressure. You've got a certain amount of pressure outside, the ambient or external air pressure, and you have a higher internal or cabin air pressure, and that gives you a pressure differential. So cabin differential pressure is the difference between the ambient or external air and the internal air pressure. The cabin differential pressure can be measured on the cabin differential pressure gauge. It's got nothing whatsoever to do with mean sea level, and it does not measure the cabin pressure controller setting. Now, when you pressurize an aircraft, you impose stress on that aircraft, and the kind of stress you impose is called tension stress. When that aircraft is pressurized, what you have is higher pressure air inside the aircraft than there is outside in the ambient atmosphere, and it's pressing outward on the fuselage, and that kind of stress is called tension stress. And you can measure how much stress you're putting on the aircraft by how much the cabin differential pressure is. Now, the fuselage is designed to only take a maximum amount of differential pressure because it can only take a certain amount of stress. And one way to get rid of excess pressure, if it looks like you're about to get it, is to open the dump valve. The purpose of the dump valve in a pressurization system is to relieve all positive pressure from the cabin. So when you open the dump valve, basically you've taken the cabin to normal atmospheric pressure, whatever that may be, and you've gotten rid of the differential, the pressure differential, and you have relieved the positive pressure from the cabin, and that gets rid of the stress on the aircraft. Now, a pressurized aircraft is designed to take tension stress, which means stress from the inside of the aircraft pushing out with higher pressure air inside the aircraft than surrounds it. It is not designed to take negative pressure, and so aircraft have a negative pressure relief valve in the pressurization system, and what that does is it prevents the cabin altitude from becoming higher than the actual altitude of the airplane. Another way to put that is it prevents the pressure inside the aircraft cabin from being lower than the ambient atmospheric pressure around it. It prevents having pressure press inward on the aircraft as opposed to having it press outward the way that a pressurized aircraft is designed to do it. So it prevents the cabin altitude from becoming higher than the airplane altitude, and the way it does that is simply lets ambient outside air in if the cabin altitude is getting higher than the actual airplane altitude is. Now, in general, it's not a good idea to have a cabin pressurized when you're on the ground. So to avoid that happening, the main landing gears on many aircraft will have a micro switch on them, and that micro switch prevents the cabin from being pressurized on the ground. So the pressurization is prevented by the pressurization main landing gear operating switch. Basically what happens is that when the oleo compresses, indicating that there's weight on the wheels, therefore that you're on the ground, that switch will make sure that the cabin is not pressurized, and that allows you to open the cabin door more easily, and also make sure that when you do open the door, you don't get blown out of it because the cabin is pressurized. It's not done by regulators or relief valves in the cabin, but by that pressurization engine main landing gear operating switch. Now, what exactly constitutes a pressurization cycle in an aircraft? Well, a pressurization cycle is considered to be one complete series of events or operations that occur regularly in the pressurization system. It is not one takeoff and landing, because it could be a very short, low-altitude flight where you don't pressurize at all. And it is not reaching maximum pressure differential in the aircraft, because if it's a low-altitude flight, you might not get all the way to max pressure differential. It's one complete series of events or operations that recur regularly in the pressurization system that constitutes that pressurization cycle. Now, cabin pressurization is based on, one way or another, stuffing a lot of air into the aircraft cabin and then controlling the outflow of that air out of the back of the cabin. One way to stuff a lot of air into the cabin, particularly used in large piston engine aircraft that are going to be pressurized, and also in some of the earlier jets that didn't have all that much engine power, is an independent cabin air compressor. Now, an independent cabin air compressor may use bleed air from a turbine engine in order to operate the compressor, or it can be gear driven through an accessory drive gearing off of the engine. But in either case, what that cabin air compressor is doing is, whether it's powered by bleed air off the engine or whether it's powered by an accessory gear drive, that compressor is independently pulling air in from outside and taking that air and compressing it and putting it into the aircraft cabin. It is not taking bleed air directly from the engine and putting it into the cabin. If the compressor is driven by the engine, it's still pulling in outside air and using that, compressing that, and putting it into the aircraft cabin. Now, sometimes these independent cabin air compressors can become disengaged or quit functioning for one reason or another. And if that happens, you do not want to lose the pressurization air. And that is prevented from happening by a check valve in the delivery air duct. So when they ask you if the cabin air compressor becomes disengaged, what prevents a loss of pressurization, it's not valves in the back of the airplane they're talking about. What it is a check valve in the delivery air duct that keeps the air from coming back out through the compressor if that cabin air compressor becomes disengaged. Okay, the independent cabin air compressor like that is typically what you would find on a large piston engine aircraft to pressurize the aircraft. But if you're working with a jet aircraft, what you're typically going to be using is bleed air instead. They take air, hot compressed air, off the compressor section of the turbine engine, and that provides bleed air for the pressurization and air conditioning systems of a jet aircraft, because modern jet engines have more than enough air, not only for the engine operation, but also for the cabin air system, for the cabin pressurization. And you can use that bleed air from the turbine engine compressor because generally it is free from contamination and can safely be used for cabin atmospheric air. Now, in a pressurization and air conditioning system, you very commonly will have a jet pump in the system. And the purpose of the jet pump, when you've got it, is the same idea that a jet pump provides in a fuel system, only it's working with airflow instead of fuel flow. What it does is augment the airflow in some areas of the aircraft. And the way they do that is they take high pressure, high volume bleed air, and they run it through this jet pump. They run the high pressure air through the jet pump and use that to pull in other air, a high volume of air under lower pressure. So the jet pump is used to augment the airflow, get more airflow in some areas of the aircraft. Now, you want to be able to control the cabin pressurization, so here's the pressurization control panel in a 727. A pressurization controller has three things that it really has to have in order to be able to control the cabin pressure the way that the pilot wants it. And that is barometric pressure, cabin altitude, and cabin rate of change. Barometric pressure is the ambient outside pressure. Cabin altitude is the pressure inside the cabin, and then cabin rate of change is how fast the cabin is going up or down, and those three inputs allow the pressurization controller to do what the pilot wants. Now, as part of that pressurization control system, there is a cabin pressure regulator, and the cabin pressure regulator is controlled by cabin air pressure. In other words, you basically say, I want the cabin to be this altitude, and then by knowing what altitude the cabin air pressure actually is, the regulator will open or close the outflow valve in the back to keep the cabin pressure where you want it. We're going to talk about that outflow valve a lot more in just a minute. The cabin pressurization system, or ranges, have basically three modes or ranges of operation. What you've got in that cabin pressurization system is an unpressurized mode, a differential mode, and an isobaric mode. Unpressurized, differential, and isobaric. Unpressurized is pretty obvious. Unpressurized basically is you don't have the pressurization system working at all. Whatever air you've got in the cabin is the same as ambient, normal outside air, and that's what small general aviation aircraft have got. No pressurization at all. The isobaric range. The isobaric range means that you are controlling the cabin altitude, you are controlling the actual pressure in the cabin. You have it set for 5,000 feet of altitude or 8,000 feet of altitude or whatever actual cabin altitude you want. The differential range on the pressurization controller means that you can no longer control the actual altitude of the cabin because the aircraft is high enough that that would give too much pressure differential. So in the differential mode, what the pressurization system is controlling is the differential between the pressure inside the aircraft and the pressure outside the aircraft and maintaining the maximum differential that is allowed. And whatever the cabin altitude works out to be, that's what it'll work out to be by keeping the differential pressure within the range that the aircraft is allowed to carry to keep from overstressing the aircraft. Now, we've been talking about the outflow valve. Basically, what the outflow valve does, and located in the back of the pressurized aircraft, is controls the pressurization, the cabin pressure on an aircraft. And the way it does that is it gets rid of all the cabin pressure in excess of the amount for which it's set. So what you're doing is stuffing air in the front of the cabin, either by bleed air off the engines or through an independent cabin air compressor, and then this outflow valve in the back of the cabin will dump any air over the amount that you have called for in the pressurization controller. So what really controls the pressurization of an aircraft cabin is the outflow valve, not the input coming in, but how much air you allow to go out the back of the aircraft through that automatic outflow valve. So the primary function of the outflow valve is to maintain the desired cabin pressure. That's the primary function of the outflow valve. And as you can see by that, the cabin pressure control setting is going to have a very direct influence on the outflow valve opening. If you ask for a higher cabin altitude, then that outflow valve is going to be open more to let more air out so that you don't have as much air pressure in the cabin and you have a higher cabin altitude. Now let's assume that you're climbing to altitude, but the cabin rate of climb is too great. You're looking at the cabin rate of climb indicator in the pressurization system, and the cabin is climbing too fast. The cabin rate of climb is too great. What the FAA says do you want to do about that? The pressurization control should be adjusted in that case to cause the outflow valve to close faster. If the cabin is climbing too fast, it means that too much air is going out the outflow valve in the back, not enough is staying in the cabin, and that means that outflow valve needs to close faster, needs to get more closed quicker, and that will retain the air in the cabin and slow down the rate of climb of the cabin. So close the outflow valve faster if the cabin is climbing too fast. Pressurization is wonderful. But what if you don't have pressurization? or you just simply need a backup system. In that case, we use an oxygen system. This guy has not only got his oxygen mask on, he's also got smoke goggles on, but the oxygen is what you would have to use if you either did not have a pressurized aircraft and you're flying at altitude, or for some reason the pressurization system failed. Now, the oxygen that is used in aircraft systems is not the same as medical or hospital quality oxygen. The oxygen used in aircraft systems is 99.5% pure. It is water-free for all practical purposes. And the reason we say it's not hospital quality is because hospital or medical quality oxygen usually contains water, and you do not want water in aircraft oxygen systems. The primary difference then between aviation breathing oxygen and most other types of commercially available oxygen is the amount of water, the amount of moisture in it, because the aviation breathing oxygen has had the water and the water vapor removed. Now, if you're going to install a high-pressure oxygen cylinder in an airplane, that high-pressure oxygen cylinder has to meet certain specifications. And those specifications it has to meet are the ones of either the Interstate Commerce Commission or the Department of Transportation. Both the Interstate Commerce Commission and the Department of Transportation have specifications for high-pressure oxygen cylinders, and the cylinder has to meet one of those two sets of specifications. High-pressure cylinders, by the way, that do contain oxygen for aviation use can be identified pretty easily because, first of all, they're green, and secondly, they're going to have the words aviators breathing oxygen stenciled on them in 1-inch white letters. So they're very recognizable and very identifiable. Now, when you're working with a built-in oxygen system in an aircraft, in some of those systems, you will have a pressure reducer valve. And the whole purpose of the pressure reducer valve in the system is to change the high cylinder pressure, because in the cylinder you've got pretty high oxygen pressures, 1800 psi and so on, down to low pressure for the oxygen system as it goes through the aircraft. If that pressure reducer fails, what will happen is a pressure relief valve will prevent high-pressure oxygen from entering the system downstream. Basically, what it will do is it will blow out the oxygen out plugs in the fuselage skin, because that way the high-pressure oxygen will get vented overboard rather than going through the system and creating problems in a system that is designed to take low-pressure oxygen as opposed to high-pressure oxygen. And this is what that plug looks like that you'll find on the fuselage skin. If that green thermal expansion disc is missing, that means that you may have had an overpressure event in the aircraft oxygen system. Remember, disc is on the outside of the fuselage. It is not in the cockpit or on the oxygen regulator. Now, if you're flying in a normally unpressurized aircraft, normal, small general aviation aircraft, something like that, the oxygen systems are generally of the continuous flow or pressure demand types. The continuous flow oxygen system uses the rebreather bag principle. So in this continuous flow oxygen mask, you've got oxygen coming in through a tube, but as the person breathes in and out, that breath is collected in this rebreather bag here, so that as you breathe each time, you're not getting pure oxygen, you're getting oxygen that is mixed in with normal air, and that gives you less of a concentrated mixture. The continuous flow oxygen system uses a rebreather bag principle. Now, how do you control the amount of oxygen that's going to be delivered to a mask like this? A calibrated orifice in the system. In other words, where that mask plugs into the aircraft oxygen system, there will be a calibrated orifice, a hole of a certain size, and that controls the volume of oxygen, the amount of oxygen that will be delivered to that mask. Now, the type of mask that the crew would typically use, and particularly in an aircraft that is normally pressurized, is a diluter demand oxygen regulator system. In the diluter demand oxygen regulator system, whenever the user breathes, the demand valve operates. In the other system, the continuous flow, the oxygen does just what its name says. It flows all the time. In the diluter demand system, you only get oxygen when the user breathes, and that is much more conservative in the use of oxygen because you don't have it flowing out into the atmosphere when the person isn't breathing and isn't using it. Now, you will have very typically an airflow metering aneroid in the demand regulators on this type of oxygen mask. And the purpose of that airflow metering aneroid is to regulate the airflow in relation to the cabin altitude when the mask is set in the diluter demand position. Bunch of words there. What exactly does it mean? A mask like this can be set for either normal, what they call the diluter demand position, or it can be set for 100% oxygen. Most of the time, at most altitudes, you do not need 100% oxygen in order to have adequate oxygen because there is a certain amount of oxygen in the air. So what it's got is an aneroid in the demand valve here, and what that does is it senses the outside pressure, and then it allows a certain amount of ambient outside air to come in when you breathe on the oxygen so that you get some oxygen and some outside air, and the amount of outside air is reduced and the amount of oxygen from the mask is increased as you go to a higher and higher altitude. So that aneroid regulates the airflow, the ambient airflow, in relation to cabin altitude when it's in the diluter demand position. Now, sometimes it's useful to have an oxygen system for emergency or backup use. And sometimes that emergency or backup oxygen will be a chemical oxygen candle system. A chemical oxygen candle system is the least complicated and requires the least maintenance as far as an emergency or backup use is concerned. The basic problem with it is once you start that kind of oxygen going as a backup, you're going to go all the way through that chemical oxygen candle. There isn't any way to shut it off or stop it once you start it. So you're going to use it all up in that particular time. But it's not complicated and requires very little maintenance. So the characteristics that you have of a chemical or solid-state oxygen system are that you've got a lot of storage capacity. You have a volume storage capacity of about 3 times that of compressed oxygen. That's one of the advantages of that solid-state oxygen system as a backup. And also, the system generators are inert below 400 degrees Fahrenheit, even under severe impact. What that means is that you're not going to have an explosion, you're not going to have a fire problem with it as long as the temperature is below 400 degrees Fahrenheit, even if you have a crash, if you have a severe impact. So it's a safe way to go, and it's got a lot of oxygen volume. Another alternative for an oxygen system has been used in military aircraft, although not in civilian aircraft yet, and that is mechanically separated oxygen system. A mechanically separated oxygen system uses a molecular sieve, and what that molecular sieve does is basically filter out the oxygen and put it into the system and reject the other gases in the air, and that creates basically, or separates oxygen from the air, a mechanically separated oxygen system. Now, there's some very important things to know about oxygen system maintenance, some precautions that you have to observe if you're working on an oxygen system. First of all, any tools and any equipment that you're using to service oxygen must be kept free from oil and grease. Oxygen is very flammable, and you can get spontaneous combustion if you have anything that has oil or grease on it around the oxygen system when you're working on it. You want to make sure that you display no smoking placards when you're working on the oxygen system because, again, oxygen is extremely flammable. Because of that, you want to make sure to provide adequate firefighting equipment in the area when you're working on an oxygen system. And you do not want any sparks, so you want to avoid checking aircraft radio or electrical systems. You don't want any sparking problems. Now, you may need to check the serviceability, determine the serviceability of oxygen cylinders. They have to be the correct type, and they have to have been hydrostatically pressure tested with water within the proper time interval. And what hydrostatically tested means is that they put water pressure inside it and pump it up to see if the thing cracks or breaks, and when they take it up to the pressure limits that they're supposed to for proper testing. A high-pressure oxygen cylinder has to be hydrostatically tested every 5 years. A standard weight high-pressure cylinder needs to be tested every 5 years. Now, how do you know if an aircraft oxygen bottle can be considered airworthy? Well, it has to have been hydrostatically tested, and it needs to have 3 things stamped on the cylinder near the neck of the bottle. And those 3 things are the test date when it was hydrostatically tested, the DOT number, and the serial number of the bottle. What does not have to be stamped up there is the manufacturer's name. The manufacturer's name is not one of the required 3 items. Now, in addition to standard bottles, there are also lightweight cylinders, known as a DOT 3HT oxygen cylinder. They get less time between hydrostatic testing. They have to be hydrostatically tested every 3 years instead of every 5. And on the lightweight cylinders, they have to be retired from service after 24 years or after 4,380 filling cycles, whichever one occurs first. So they get a long life, 24 years, but they don't get an awful lot of filling cycles, only 4,380. On the other hand, a third type of oxygen bottle, a composite oxygen bottle that conforms to DOT E8162, has a service life of only 15 years, but on the other hand, it gets 10,000 filling cycles, whichever one comes first. Now, the FAA will try and mix you up between the requirements as far as the lightweight cylinders, the 3HT cylinder, and the composite oxygen bottles are concerned. The lightweight cylinders have a longer life, 24 years, compared to 15 years for the composite, but on the other hand, the composite bottles have more than double the filling cycles, 10,000 filling cycles for the composite bottles. So think of the composite bottles as having lots of nice round numbers, 15 years of service life, and 10,000 filling cycles, whichever one comes first. Composite oxygen bottles, by the way, are aluminum bottles that are wrapped with Kevlar. Now, how do you determine how much oxygen you've got in a portable high-pressure cylinder? Well, the easy way when you're working with a portable cylinder is to read the pressure gauge. Simply read the pressure gauge that is mounted on the cylinder. you want to make sure that it's always got some pressure in it, because if oxygen bottle pressure is allowed to drop below a specified minimum, what can happen is moisture can collect in the bottle, and that can result in corrosion and some other problems. The main cause of contamination in a gaseous oxygen system is moisture. Moisture can cause corrosion. Moisture in an aircraft oxygen system can also freeze at altitude and plug up the whole oxygen system. So you want to make sure that there's pressure maintained in the system, and that's why the problems with moisture is why aviators breathing oxygen is moisture-free, unlike medical oxygen. Now, if you have a contaminated oxygen system, normally it is purged with oxygen. If you need to purge it, you purge it with oxygen. If you have to use something as a lubricant on the oxygen system tapered pipe threads, you do not use normal oils and greases and so on. What you can use is Teflon tape. Teflon tape is what you can use as a lubricant on the oxygen system pipe threads. Now, if you suspect that the aircraft oxygen system has a leak in it, the way you test it, the lines and fittings, is by bubble testing with a testing soap solution that is made specifically for that purpose. So you can bubble test it with a soap solution. What you don't want to do is run around with matches trying to see if you get any flame off, because boy, you could sure get quite an explosion if you really do have a leak in the oxygen system. Now, another way to check for leaks is to use a pressure temperature correction chart. So take a look in the FAA's Appendix 2, and when you get to Appendix 2, you'll see Figure 14, which is a pressure temperature correction chart. Now, before you start working one of these charts, it's important to take a look at all the labels and see what everything is you're working with. Up the left-hand side of that chart is change in temperature in degrees Fahrenheit. That's not the actual temperature. That is the change in temperature. On the right-hand side of the chart, going from bottom to top, is change in temperature in degrees Celsius, and across the bottom of the chart is change in pressure in psi, pounds per square inch. So what we're going to have to know in order to find out how much pressure change is allowed with a change in temperature is what the temperature change was, not so much what the absolute temperature is. Okay, so what's the FAA going to say to you? They're going to say to you that 1 hour after an oxygen system was charged to do a leakage check, the oxygen pressure gauge read 460 psi and the temperature was 63 degrees Fahrenheit. Okay, one thing we know right there, we're going to be working with degrees Fahrenheit as far as our temperature is concerned. Now, 6 hours later, the temperature had decreased to 50 degrees Fahrenheit, and they want to know what pressure gauge readings would be acceptable to remain within the allowable limits, and they throw in the fact that a 5 psi change is the maximum allowed in a 6-hour period and still have an acceptable leak test. What they're basically saying is that when the temperature changes, the pressure will also change even if you do not have a leak, and on top of whatever pressure change you're allowed due to the change in temperature, you are allowed a 5 psi difference as far as leak is concerned in a 6-hour period and still have it pass as far as a leakage check is concerned. Okay, to get the solution to this, the first thing we need to do is take a look at the numbers as far as the temperature is concerned. When you took the first reading, the temperature was 63 degrees Fahrenheit. When you took the second reading, the temperature was 50 degrees Fahrenheit. The difference is 13 degrees Fahrenheit lower. So the temperature has decreased by 13 degrees. The pressure can also decrease since the temperature decreased by some amount, and we'll have to find out how much. To find out how much, we take a look back at Figure 14 again. On the left-hand side of the chart for change in temperature in degrees Fahrenheit. The change in temperature was 13 degrees. So here is 10 degrees. The next major line is 15, although it's not labeled. The line above that is labeled as 20 degrees of temperature change. We're looking for 13. So we start at 13 degrees of temperature change, and we come straight across to the right until we hit that straight diagonal line. And when we hit that straight diagonal line, we turn and drop straight down to the bottom of the chart, which will tell us what the allowable change is in pressure. And the 10 line, vertical line, is labeled, the 15 line is not, and the next labeled line is the 20 psi line. And so where this arrow comes down, boy, it's awful close to the 10, but not quite on it. It looks like about a 10.5 psi change in pressure would be allowed with a 13 degree change in temperature based on this chart. Okay, here's what the numbers look like then. In order to determine the allowable pressure at 50 degrees Fahrenheit, what we do is take the pressure reading we had of 460 psi at the original temperature, 63 degrees, and we subtract the 10.5 psi that the pressure is allowed to be lower because the temperature is 13 degrees lower. And what that tells us is if there were no leaks whatsoever, we should have a system pressure at 50 degrees Fahrenheit of 449.5 psi. 449.5 psi. That would be if there were no leakage whatsoever. But we are allowed a little bit of leakage. Remember, they said you're allowed a leakage of 5 psi over a 6-hour period. So if you take that 449.5 that it ought to read if there's no leakage and subtract the 5 psi allowable leakage, then the minimum reading that you would have would be 444.5 psi. So the allowable reading that you could have at the lower temperature would be 445.5 to 449.5 psi, depending on whether you had any leakage or no leakage, or if you round those off, as the FAA will on the test, the allowable readings would be from 445 psi to 450 psi. 450 psi if you had no leakage at all, 445 psi if you had the maximum leakage that the system does allow. Okay, let's talk now about air conditioning systems. And there's basically two types. When you're working with jets like 727s and so on, typically you're going to have an air cycle cooling system. The other type of cooling system is a Freon system, and we're going to talk about that in just a minute. The basic air cycle cooling system consists of three things. You've got a source of compressed air, which would normally be bleed air off the engines, but could also be an independent cabin compressor. You've got heat exchangers to get rid of the heat out of the air, and you've also got a turbine, an expansion turbine, that's going to cool the air down even more. To understand those components a little bit better, let's take a look at a diagram of the air conditioning system in a 727. This is the schematic of the air conditioning system in a 727, and the airflow comes in from the bottom. So we have a source of compressed air. In the 727, it's coming off the engines, but again, in other airplanes, it could be an independent cabin system. The hot air comes in from the engines, and it comes over here, and it goes through a primary heat exchanger. Then it continues on along and goes through a compressor, or runs a compressor, continues on along, goes through a secondary heat exchanger, continues on and gets to here, which is the expansion turbine, which is a very critical, important part of the air cycle cooling system, because the air cycle cooling system basically produces its cold air by extracting heat energy across an expansion turbine. When that air moves through this expansion turbine, it cools off very quickly, and that's what provides the cold air for the cabin. So the air in the expansion turbine undergoes a pressure drop and therefore a temperature drop when the system is operating. As it goes through this expansion turbine, you get both a pressure and temperature drop, and that's what gives you the cold air. And from there, it goes on to a water separator to get the air out, and after it goes through the water separator, then it goes into a mix valve. And the purpose of that mix valve in the air conditioning system is to control the supply of hot, cool, and cold air, because it's got cold air, it's got medium temperature air, and it's got hot air going into it, and the various valves mix them in order to get exactly the temperature of air that you want based on how the mixing valve is set. Okay, that's basically the air cycle cooling system in an aircraft. Now, a lot of aircraft have a Freon vapor cycle cooling system instead of, or sometimes in addition to, an air cycle cooling system. And the Freon vapor cycle system is the basically as you would have in a house or you would have in a car. If you take a look on FAA page 55 at figure 13, you'll see a schematic of a Freon air conditioning system, and that figure 13 will be available to you on the test. And it's very useful even for questions where they do not specifically refer you to it, because the schematic tells you about what's going on and what's happening to the Freon as it moves through the system. And notice there's a key in the upper left corner. Now, the FAA keyed it just with different types of lines and hatchings, but we colorized it in order to help make it a little bit more readable as we talk about it. Our orange line is low pressure vapor. Our kind of purplish pink line is high pressure vapor. Our blue line is low pressure liquid, and the green line is high pressure liquid. And let's take an overall look at the Freon as it moves through this Freon air conditioning system. Starting in the lower left hand corner, a general look at what's happening. It moves through a receiver and dryer. It comes on around. Here it is high pressure liquid, moves through the expansion valve, becomes low pressure liquid, moves through one of the two units that is not labeled. And so we're going to label them here for you. The center unit is the evaporator. The bottom unlabeled unit down here is the condenser. So as the low pressure liquid Freon moves through the evaporator, cabin air blows over it, and that's what cools the cabin air. And the Freon leaves the evaporator as a low pressure vapor, the orange line here. The low pressure vapor goes into the compressor, becomes compressed, and logically enough becomes high pressure vapor, comes out of the compressor as high pressure vapor and goes into the condenser. In the condenser, ambient outside air is blown over it. The Freon is cooled off and condensed back into a high pressure liquid, and then goes on through the basically the storage area, the receiver and dryer, and back on through and around in the system. Okay, we've got a generalized overview of what's happening. Let's zoom in and talk about different components and see what the FAA is going to be asking you about. First of all, in the lower left corner here, let's talk about the receiver dryer. Now, one of the functions of the receiver dryer in the vapor cycle cooling system is a reservoir for the refrigerant. So this is where excess refrigerant, excess Freon is going to be stored. If you get water, even a small amount of water, in the vapor cycle cooling system, it can freeze in the receiver and stop the entire operation of the Freon system. So we're going to take precautions when working with a system to avoid getting water in it because it can freeze in the receiver, as well as another place that we're going to talk about. Now, this particular system does not have a subcooler, but in some systems you have a subcooler, and if you've got that, the purpose of it is to cool the Freon to prevent premature vaporization. If it vaporizes too soon, it's not going to have the cooling effect in the proper place, and that's the function of the subcooler, to prevent premature vaporization. What we do have in the upper left-hand corner of this is an expansion valve. So as the high-pressure liquid Freon moves on around in the system, let's take a look at the upper left-hand corner of our schematic and see the expansion valve. And when we get to the expansion valve, notice that the high-pressure liquid Freon goes through the expansion valve and comes out as low pressure but still liquid Freon. So the function of the expansion valve is to act as a metering device and also to reduce the pressure of the liquid Freon. It goes from high pressure to low pressure as it moves through that expansion valve. One of the things that's going to happen when that occurs is that the temperature of the Freon will decrease. The Freon is going to get colder on the output side of the expansion valve, so you should be able to see a temperature difference between the two sides of the expansion valve. The position of that thermostatic expansion valve is determined by the temperature and pressure of the Freon in the outlet of the evaporator, because after the Freon goes through the expansion valve, it goes through the evaporator, and what the temperature and pressure of it is it's leaving the evaporator, controls this expansion valve, and tells it how much of the liquid Freon to allow through. Now, when this vapor cycle cooling system is operating, and the FAA, by the way, will sometimes call it vapor cycle, sometimes call it Freon cycle, means the same thing. If the two lines that are connected to that expansion valve are essentially the same temperature, then it means the expansion valve is not metering the Freon properly, because there should be a temperature drop as that Freon moves through the expansion valve, and if you don't have a temperature drop, then the expansion valve is not working properly. Now, the expansion valve is the second place where water is very, very likely to freeze in a Freon vapor cycle cooling system. So if the vapor cycle cooling system will not take a charge, you're trying to recharge it with Freon and it will not take a charge, the most likely thing that's at fault is the expansion valve, that water has frozen in the expansion valve and is not allowing Freon to go in and through the system, because it's very easy for it to plug up there. Okay, after the liquid Freon, low pressure liquid Freon, leaves the expansion valve, what it goes through next is the evaporator. Now, when you look at an evaporator in an airplane, the function of the evaporator in the Freon cooling system is to lower the temperature of the cabin air, because what will happen is that air is blowing across that evaporator and then into the cabin, and it is cooled off by the cold Freon, liquid Freon, that's moving through that evaporator. So the purpose of it is, the evaporator is, to lower the temperature of the cabin air. The way it does that is by blowing the air across the evaporator, and that air picks up the cold from the Freon. The Freon in turn picks up the heat from the air, and that changes the Freon from a liquid to a gas. So when the FAA says to you, where does the Freon in the system change from a liquid to a gas, it's as it goes through the evaporator, because it picks up the heat from the cabin air flowing over it. Comes into the evaporator as a low pressure liquid, goes out of the evaporator as a low-pressure vapor, because it's picked up the heat from the cabin system. So the condition of the refrigerant as it enters the evaporator is what? Liquid or vapor coming into the evaporator? It is a liquid. Is it a high-pressure or low-pressure liquid? It is a low-pressure liquid. And as the Freon leaves the evaporator, now is it a liquid or a vapor? Now it's a vapor. Is it a high-pressure or low-pressure vapor? It is still low pressure, but now it's a vapor instead of a liquid. Okay, the FAA is going to give you this figure in its uncolorized version, figure 13, and what they're going to ask you is, where are the evaporator coils located in a Freon cooling system? And remember, in the actual FAA figure 13, they do not label either the evaporator or the condenser, but the way that you know where the evaporator is because the evaporator has cold air coming out of it, which is cooling the cabin, and the evaporator coils are located immediately downstream in the system of the expansion valve. Immediately downstream in the system of the expansion valve. Now, in this system, if you have frost or ice buildup on the vapor cycle cooling system evaporator, if you have frost or buildup on that evaporator, the probable cause is inadequate airflow through the evaporator. For some reason, you're not getting enough airflow through there to absorb the cold of the Freon, and that's letting frost or ice build up on the evaporator. The FAA will ask you what the normal operating pressures should be if the evaporator temperature is 40 to 50 degrees Fahrenheit. And the low pressure should be about 20 to 30 psi, and the high pressure in the system should be about 225 to 300 psi. 20 to 30 psi low pressure, 225 to 300 psi for the high pressure. Now, the next unit in the system is the compressor. And the compressor in a small general aviation aircraft, as you can see here, is belt-driven. It's actually driven by the aircraft engine through a belt drive. And what the function of that compressor is, you can see when you take a look at the schematic. And what the compressor does is it takes the low-pressure vapor that came out of the evaporator and compresses it and turns it into high-pressure vapor and sends the high-pressure vapor on to the condenser, which is the next component in the system. Okay, what is the function of the condenser? What the function of the condenser is to transfer heat from the Freon gas to the ambient air, to transfer heat from the Freon gas out to the ambient air. And you can see that pretty clearly if you take a look at a condenser on an airplane. You can see hanging down off the belly there into the airflow, and that ambient airflow going over it pulls the heat out of the Freon gas. So in the Freon vapor cycle cooling system, what's used for cooling air for the condenser is simply ambient, outside atmospheric air. Now, the point in the system where Freon gives up its heat and changes from a gas to a liquid is as it goes through this condenser, because it comes into the condenser as a high-pressure vapor, and it gets cooled off, and it goes out of that condenser as a high-pressure liquid. But it goes from a gas to a liquid, and it gives up its heat in the process. So the refrigerant, as it comes into the condenser in a vapor cycle cooling system, when the refrigerant comes into that condenser, is it coming in as a vapor or a liquid? Which one? It's coming in as a vapor, and is it a high pressure or a low pressure vapor? It is a high pressure vapor coming in. And when that refrigerant leaves the condenser, is it a vapor or a liquid then? It goes out as a liquid because it's been cooled off, but is it high or low pressure? It's still high pressure, but it has gone from a vapor to a liquid when it's cooled off going through that condenser. Now, when you're servicing air conditioning, one of the things you take a look at is the sight gauge, which is just over a little bit to the left of the condenser there. If the liquid level sight gauge shows a low Freon charge, what you need to do is operate the system for a period of time to get a stable condition and then recheck the level. Before you start adding Freon or anything, let the system run for a while, 5 minutes or so, in order to stabilize and recheck that sight glass. Now, what are you looking for? If you see a steady stream of bubbles going through that sight glass, it means that the Freon charge in the system is low. Same as it does on a sight glass in a car air conditioning system. If you see a lot of bubbles going through, the Freon charge is low. Now, when you're charging the system, the way you tell when you've got the proper amount of Freon in it is air bubbles disappear. So when you're looking at that sight glass as you charge the system, when the air bubbles disappear, what that means is you've now got the proper amount of Freon added to the system. Now, when you are adding Freon to the system, normally you're going to be adding Freon vapor, and you would want the can to be vertical with the outlet up at the top. But suppose instead that you want to add liquid Freon to the system. You got to do it differently. When you're adding liquid Freon to the system, you place the bottle vertical still, but this time the outlet has to be down at the bottom in order to put liquid into the system. Now, you can damage the compressor in a Freon system if liquid refrigerant is introduced on the low side of the system, if pressure is too high, or if the outside air temperature is too low. So you want to be careful about putting liquid Freon in, but if you are going to do it, the bottle needs to be vertical with the outlet down at the bottom. Now, when you're working with Freon 12, which is the refrigerant that you normally would use, goggles should be worn because even a little bit in your eyes can be very damaging. Something else to be aware of about refrigerant 12 is that if you have it over an open flame, if it passes over an open flame, it changes to phosgene gas, and phosgene gas is very, very deadly. So when you're working with the air conditioning system, working with refrigerant, you do not want to have any open flames around. Now, if you're servicing an air conditioning system that's lost all of its Freon, what you need to do first is check the oil and add any that's necessary, then evacuate the system, and then add Freon. The purpose of evacuating the Freon air conditioning system is to remove moisture. And remember, moisture does a couple of things. First of all, the moisture can freeze in the system and basically just shut it down. And in addition to that, if you've got water in the system, it will react with the refrigerant and form hydrochloric acid. And hydrochloric acid will be very corrosive to the metal in the system. So water can both freeze and shut the system down, and it can also form hydrochloric acid, which will corrode the system. Okay, so we know why we need to evacuate a Freon air conditioning system. Now let's talk about how we do it. The way you evacuate a vapor cycle cooling system is what you do is attach a vacuum pump to the system. That vacuum pump lowers the pressure, and by lowering the pressure, it lowers the boiling point of the water, turns the water into vapor, and then can draw out the vapor. So what you need to know for the test is that the evacuation of a vapor cycle cooling system, the way it does it is by lowering the boiling point of the water and pulling out, drawing out the vapor. So when you're purging the Freon air conditioning system, you need to release that charge very slowly. Release the charge at a very slow rate, and the purpose of doing it at a slow rate is you do not want to lose the refrigerant oil. You want to keep that refrigerant oil in there. Now, when a vapor cycle cooling system is not in operation, one of the ways to tell whether it's leaking or not is to look for oil seepage. Oil seepage is an indication the system is leaking Freon. You will not see the Freon itself because the Freon is colorless. But the oil is contained in the Freon, and if you see oil seepage, you know that you've had some Freon leakage. When you need to put oil back in the system, what you have to use is special refrigeration oil. Special refrigeration oil is the only oil that's suitable for use in Freon air conditioning systems. Now, when you're recharging a Freon system, what you're going to have done is evacuated the system using a vacuum pump. You've got gauges on both the low pressure and high pressure side of the system. If the low pressure gauge fails to come out of the vacuum that you had when you evacuated it, if it fails to come out of the vacuum as you're charging the system, it means that you've still got some kind of blockage in the system. It means that you've got a blockage somewhere in the system. Okay, that's enough about air conditioning. let's talk about heating systems. First of all, let's talk about combustion heaters. Combustion heaters in aircraft can range all the way from a small nose-mounted unit to heat the cabin of a small aircraft, twin-engine aircraft, or they can be combustion heaters in large piston-engine aircraft that not only heat the cabin but also provide hot air to heat the leading edge of the wing. The operation of a combustion heater in an aircraft is controlled by a thermostat circuit which basically turns the fuel on and off, and that's a process known as cycling. So basically the way that the combustion heater is controlled is the thermostat simply turns the fuel on and off. It cycles the heater in order to get and keep the air however hot you've asked for it to be. Now there's two types of air that are used on a combustion heater. You've got the combustion air that goes right into the combustion heater and is used in the combustion process. But much more important as far as volume is the ventilating air. The ventilating air is basically air that goes around it in a heat exchanger sort of way, and the ventilating air gets warmed and carries the heat to the places where it's needed, whether it's the leading edges of the wing to anti-ice them, or whether it's the cabin to heat the cabin. The ventilating air is what carries the heat to the places where it's needed. Now, you've got one of two ways in order to prevent too much air from getting into the heater as the air pressure increases. You have a combustion air relief valve, or you've got a differential pressure regulator. Either one of those, it does not have to have both, either one of those in a combustion heater will keep too much air from entering the heater when the air pressure increases. Now, if you've cleaned or replaced the filter element in the fuel system on a combustion heater, you need to be very sure to pressurize the system and check all of the connections for leaks. Because if a combustion heater starts leaking fuel, you've got a real fire hazard there. So you want to pressurize the system and make sure that you don't have any leaks at the connections if you've broken the system, if you've cleaned or replaced the filtering element. Now, smaller general aviation aircraft use basically a heat exchanger or a jacket around the engine exhaust as the heat source for heat for the cabin. And when you're inspecting the heating and exhaust systems on those kind of aircraft, you not only want to look at it very closely physically, but you also want to periodically do an operational carbon monoxide detection test. And the reason for that is, with the heat exchanger setup, if you get a leak in that, carbon monoxide can end up leaking into the aircraft cabin. And if you're in flight, the last thing you want is carbon monoxide in the cabin.